The idea of targeting glycogen phosphorylase in the brain might seem niche or overly technical at first glance, but it taps into a growing understanding of how tightly energy metabolism and neurodegeneration are linked. Glycogen phosphorylase, the enzyme responsible for breaking down glycogen into glucose, 1-phosphate, plays a key role in energy mobilization during times of high demand. While this function is well characterized in liver and muscle tissues, its relevance in the brain has only recently begun to draw attention, and the implications are profound. In healthy neurons and astrocytes, glucose is the primary energy source. But neurons do not store much glycogen themselves. Instead, astrocytes act as the brain's energy reservoir. These supportive glial cells store glycogen and, when necessary, break it down through glycogen phosphorylase to release glucose-derived energy substrates that can be shuttled to neurons. This process is particularly crucial during periods of metabolic stress, such as inflammation, injury, or prolonged cognitive effort, when immediate glucose supply may be limited or blood flow may be compromised. In neurodegenerative diseases such as Alzheimer's, Parkinson's, and even Huntington's disease, there is increasing evidence of impaired glucose metabolism in the brain. Neurons begin to lose their ability to efficiently use glucose, leading to energy failure, mitochondrial dysfunction, and oxidative stress. As this energy deficit worsens, it accelerates the misfolding of proteins, the buildup of toxic aggregates like amyloid beta and tau, and ultimately the death of neurons. Here, glycogen phosphorylase might represent an underexplored therapeutic target, one that could shift the brain back toward energy balance by improving the mobilization of internal glucose stores. Activating glycogen phosphorylase in astrocytes could theoretically increase the availability of energy substrates during critical periods, supporting struggling neurons. This could reduce their vulnerability to oxidative damage and limit the production of toxic byproducts that emerge when energy production is forced to rely on alternative, inefficient metabolic pathways. Moreover, restoring proper energy dynamics might help preserve synaptic plasticity and neurotransmitter function, two processes that decline early in neurodegenerative conditions. There is, however, a biological tightrope to walk here. Too much glycogen breakdown, or its improper regulation, could flood cells with glucose or glycolytic intermediates, potentially leading to harmful downstream effects like lactic acidosis or excessive reactive oxygen species, ROS. In fact, some studies have linked aberrant glycogen accumulation and disordered glycogen metabolism with neuronal stress and even neurotoxicity, particularly in rare disorders like Lafora disease. So, therapeutic activation of glycogen phosphorylase must be precisely tuned, ideally localized to the right cells, at the right times, and in the right disease contexts. The promise, though, is significant. Unlike many current neurodegenerative treatments that only address symptoms, a therapy targeting glycogen phosphorylase could intervene earlier in the disease cascade by restoring metabolic resilience. This is not just about managing glucose more effectively, it's about enabling neurons to survive longer, maintain their function, and resist the degenerative forces that are set in motion by energetic failure. Research into small molecules that selectively activate or modulate this enzyme in the brain is still in its early stages, but the concept is gaining traction. If successful, it could open a new front in the battle against diseases that currently have no cure, providing a way to reinforce the brain's own internal power grid rather than simply patching the damage once it's too late. Still, caution is warranted. Metabolic interventions in the brain require careful control, and there are significant gaps in our understanding of how glycogen phosphorylase behaves in different brain regions, across age groups, and in various disease states. Overactivation or mistargeting could backfire. But if future research can develop safe, brain-specific modulators of this enzyme, we may be looking at a new kind of neuroprotective strategy, one that helps the brain help itself by tapping into its most fundamental resource, energy.